Hi, my name is Mohana, daughter of Dakshinamurthy. My matrix number is S75239. In this video, I will present question 1 and question 2. For part A, we type the given code in MATLAB and ran it. The code generates a discrete time cosine signal x1n with amplitude 2, frequency is 0.3 pi and phase pi over 4, and plot it using the stem function. And for the part B, the length of x1 n is calculated as 60 minus 0 plus 1, which equals 61. And for part C, we check periodicity by computing 2 pi over omega, which is 2 pi over 0.3 pi, giving 20 over 3. Since this is a rational number, x1n is periodic. The fundamental period n is found at m equals 3, giving n equals 20. And for the part D, we generated x2n with amplitude 3.5, frequency 0.22 pi, phase negative pi over 3 over 60. Both signals are plotted on the same figure using the subplotted command. And for the part E, checking periodicity of x2n, 2 pi over 0.22 pi equals 100 over 11, which is rational. Therefore, x2n is periodic with fundamental period n equals to 100. Moving to the last part, which is part E, part F. Comparing both plots, x1n oscillates faster with smaller amplitude, while x2n oscillates slower with larger amplitude due to its lower frequency and higher amplitude. Moving to the question 2. For the question 2, we first ran the given example code which generates a damped complex sinusoid and plots its real imaginary magnitude and phase. Then we generate our signal xt equals 5 exponent power of negative 0.t times exponent power of j60 for t in range 0 to 6. Using Euler's formula, real part is 5 exponent to the power of negative 0.3t cos 60, and imaginary part is 5 exponent power of negative 0.3t sine 60. Figure 1 shows both oscillating with decaying envelope. Figure 2 shows magnitude smoothly decaying from 5 and phase increasingly linearly. That concludes question 1 and 2. Thank you.
A very good morning, doctor. My name is Susan Ching and my metric number is S75053. Today I would like to present question 3 and question 4. Question 3. Consider the following discrete time signal H1n, same with delta n minus 2 plus delta n minus 4. H2n, negative 1 per 3n, un plus 2 minus un minus 3. Xn equals to 1 per 2n un minus 5. All signals are defined over the range of negative 6 smaller than n smaller than 6. A. Write MATLAB code to generate and plot H1n, H2n, and Xn using subplot. First, we have H1n, which is a combination of three impulse functions: a positive impulse at n equals to 0, a negative impulse at n equals to 2, a positive impulse at n equals to 4. This is a phase signal. It's 0 everywhere except at these 3 points. Second, H2n equals to negative 1 per 3 raised to the power n, but only active between n equals to negative 2 and n equals to 2. The terms un plus 2 minus un minus 3 creates a rectangular windows from n equals to negative 2 to n equals to 2. Third, xn equals 1 per 2 raised to the power n, active only from n equals to 0 to n equals to 4. In the MATLAB code, we implement the unit function using an anonymous function, then apply it to create each signal. The subplot command allows us to see all three signals stacked vertically for easy comparison. B. Now assume a system H is formed by connecting H1 followed by H2, where Xn is the input to H1, Vn is the output of H1, Yn is the output of H2 after taking Vn as its input. Use convolution to compute Vn, same with Xn, times h1n and yn, same with vn times h2n. Plot both vn and yn using subplot. Here, we connect H1 first followed by H2. The input Xn goes into H1 producing an intermediate signal Vn. This is calculated using convolution Vn equals to Xn times H1n. Then Vn becomes the input to H2 producing the final output Yn equals to Vn times H2n. In the code, we use MATLAB built-in convolution function, then carefully compute the corresponding index vectors. Finally, we plot both Vn and Yn using subplot. C. Now reverse the order of the system, that is Xn is output to H2, output Vn equals to Xn times H2n, then pass Vn through H1, producing Yn equals to Vn times H1n, plot the new Vn and Yn using subplot. Now we reverse the order. This time Xn goes into H2 first, producing a new intermediate signal V reverse n, same with Xn times H2n. Then we pass V reverse n through H1, giving Y reverse n, same with V reverse n times H1n. In general convolution in commutative, meaning A times B equal B times A. However, that's of signal convolution. Here we have two different systems in cascade. Since convolution is associative and commutative, the overall impulse response of the cascade should be the same regardless of order. That means H total equals to H1 times H2, same with H2 times H1. Therefore, theoretical both configurations should produce the same final output Yn. Briefly explain why is Vn different in part B and C. Vn is different in part B and C because the input signal passes through a different system first. Since H1n and H2n are different systems, the intermediate output after the first convolution will also be different. Why is Yn the same in both cases? Yn is same in both cases because convolution is commutative, the order of cascading, linear, time invariant. LTI system does not affect the final output. Question 4. Write a MATLAB program to convolve the following signals. A. Plot the two signals xt and ht along with the result of the convolutions yt equals to xt times ht. Use subplot in MATLAB to display all three plots in a signal figure window. Hint: carefully define the time range so that the convolution result is accurate and properly visualized. This is a triangular pulse. The parameter beta controls the width of triangle. In our code, we use beta equals to 3 and the triangle is centered at t equals to 2. This is an exponentially decaying sine wave. The ut means it's 0 for negative time. It starts at t equals to 0 and decays as time increases. So ht looks like a sine wave that gets smaller and smaller as t gets larger. B. Analytically compute the convolution of xt and ht showing all necessary integration steps. dt equals to 0.01 sets the time step. A small value gives us high resolution and more accurate convolution. The time vector t goes from negative 2 to 10. Y start at 2. Because the triangle is centered at t equals to 2, so we need some times before it appears. We go up to 10 to capture the decay of ht. The smaller dt is the smoother our plots will be, but it also increases computation time. C. Compare the analytical result to the numerically compute one from MATLAB and explain any difference. Comment on the effect of the shape and duration of the signal on the convolution result. We need to write a MATLAB program to convolve a square wave xt approximated using its Fourier series with only odd harmonics and coefficients fracs for a and p. With a damped sine impulse response ht equals to e negative t sine t c dot ut, which starts at t equals to 0 and decays exponentially. The provided code contains several critical errors. It's incorrectly using fracs for a times n times 2 instead of fracs for a n for the Fourier coefficients. Wrongly defines ht as e negative t sine t omega 0. Instead of multiplying by the unit step function ut and attempts to plot the convolution output y against the original time vector t even though convolutions increase the signal length. The correct approach equals to 0.01 views xt by summing odd harmonics up to n equals to 21. Properly define ht using ut t gaseous 0 computes the convolutions as y takes convolution xh times dt and plots ty against the correct output time axis ty ranging from negative 20 to 20. The result shows the square wave being smooth and modulated by the decaying sine response.
Hello everyone, my name is Danish. Today we will explore frequency domain filtering and signal reconstruction using MATLAB. We'll break this down into three keys. First, how an ideal brick wall low pass filter behaves in the time domain. Second, what happens when we truncate a signal frequency spectrum. And finally, how filtering impacts the harmonic reconstruction of a periodic square wave. As you can see, this is three keys that explaining about ideal low pass filtering and impulse response, signal bandwidth and frequency truncation, and lastly for Fourier series reconstruction and harmonic filtering. Start with our ideal low pass filter H of omega. It has a constant gain of uh, 4e to the minus j3 omega within a cutoff frequency of the magnitude of omega is less than 2 and drops completely to 0 elsewhere. To find its real world behavior, we take the inverse Fourier transform. By integrating this rectangular frequency response over our limits from negative 2 to 2, the math cleanly resolves into a time-shifted sinc function, specifically 8 over pi sin of 2 times open parenthesis t minus 3 close parenthesis over pi. This shift of 3 units represent the physical phase delay introduced by the filter. Next, let's pass a signal through it. Our input is x of t equals sin of 4t, which has rectangular frequency spectrum extending up to a bandwidth of omega naught equals 4. Notice the mismatch. Our signal bandwidth is wider than our filter cutoff of uh, omega c equal to 2. When multiplied in the frequency domain, the filter aggressively chops off all high frequencies above 2. This leaves us with a truncated spectrum. Capital Y of omega equals pi e to the minus j3 omega, yielding a smoother, wider time domain output. Little y of t equals 2 over pi sin of 2 into t minus 3 all over pi. To bring this theory to life, we implement it in MATLAB. On the left, lines 3 to 4 define our time axis and calculate the filter impulse response using a tiny constant, EPS, to avoid division by zero errors. Lines 40 and 50 generate our input signal and theoretical output response. On the right side, from lines 40 to 51, we simulate a periodic square wave using a Fourier series expansion loop up to n equal 20 harmonics, applying an if condition to block any harmonic frequency that exceed our filter cutoff of 2. Finally, let's look at the simulation result. The top left blue plot display our time-shifted impulse response peaking perfectly at t equal to 3. On the right, the red input sync pulse is sharp, but after filtering, the green output response becomes significantly wider and lower in amplitude due to the lost height frequencies. At the bottom, look at our square wave reconstruction. The red wave shows the classic blocky shape, built from 20 harmonics. However, because our filter blocks everything above omega equal to 2, only the fundamental frequency passes through. As a result, the blocky square as the result as a result, the blocky square wave physically transforms into the smooth magenta sine wave you see at the bottom left. This beautifully demonstrates how frequency domain constraints reshape time domain waveforms. Thank you.
With the map to analyze the system. From the output, we can see the 0 R at S equal negative 2 and S equal 1. Why the pole located at S equal negative 4, S equal negative 1 and S equal 2. Looking at the pole 0 map, the pole are marked with red crosses and 0 with blue circle, clearly showing one pole sit in the right half plane at S equal 2. The stable function returned 0, meaning the system is unstable, which makes sense since the pole at S equal 2 lies in the right half plane. The residue from the residue function approximately first 1.667, second 0.667, and third 0.667 corresponding to pole at -4 and 2 and -1 respectively. From the output, we can see the 0 R at S equal negative 2 and S equal 1. Why the pole located at S equal negative 4, S equal negative 1 and S equal 2. Looking at the pole 0 map, the pole are marked with red crosses and 0 with blue circle, clearly showing one pole sit in the right half plane at S equal 2. The stable function returned 0, meaning the system is unstable, which makes sense since the pole at S equal 2 lies in the right half plane. The residue from the residue function approximately first 1.667, second 0.667, and third 0.667 corresponding to pole at -4 and 2 and -1 respectively. For part B, using the residue result, we derive the improved response Ht. The partial fraction expansion gives us SS as the sum of three terms, while 0.667 over S plus 4, second 0.667 over S plus 1, and 0.667 over S minus 2. Taking the inverse Laplace transform, and since the ROC is RE greater than 2, meaning causal and right side signal, the improved response is ST equal 5 divided 3 exponent power of negative 40 UT plus 2 divided 3 exponent power of negative t UT plus 2 divided 3 exponent power of 2t UT. Note that the exponent power of 2t term grow over time, which is consistent with the system being unstable. Okay, for part C, we were given the differential equation. Taking the Laplace transform, we factored the denominator as s plus 2, s plus 2, s plus 3. Note that s equal minus 2 is a repeated pole. So the transfer function is s hash equal 1 divided s plus 2 power of 2 s plus 3. The system has no zeros pole at s equal minus 2 repeated and s equal minus 3. All in the left half plane, so the system is stable. For the partial fraction expansion, we will decompose s hash into a divided s plus 3 and b divided s plus 2 and c divided s plus 2 power of 2, solving to get a equal 1, b equal negative half, and c equal 1. Finally, using the inverse Laplace transform pairs, the improved response is ht equal exponent power of minus 3t ut minus exponent power of minus 2t ut plus t exponent power of minus. The pole 0 confirms all pole in the left half plane, and the improved response plot show the system decay to 0 over time, confirming stability.